Very good morning. So last time we have started with the definition of limit, and we have been given with a function f, which is defined from the set A, or whose range is in set of real numbers. Okay, and we have let's say C belongs to A, PA, cluster point of C belongs to R, be a cluster point of A. Then we have seen when this limit extends to C, F exists and equals to L. So we have seen the definition, epsilon delta definition. Okay, but sometimes it is not possible to use epsilon delta definition because of the form of the given function f. So, okay, it may be a complicated form. So it is not easy for given epsilon at create an artificial delta. Then we have also investigate equivalent criteria. So one of them is sequential criteria. So to decide whether the limit exists or not, or if the limit exists and equals to L, and if it is exists and it is equals to L. So we have also identified sequential criteria. That is, for every sequence xn in A such that xn not equals to C for all n and xn converts to C, the sequence f of xn converges to n. Okay, so this was the sequential criteria to show that the limit exists and equals to L. So you take any sequence in A, which where each member is distinct from C, and that is converges to C. Then the sequence of the corresponding images, if you take, that converges to L. So if it is true for every sequence, then you can say limit extends to CF exists, and the limit of the sequence f of xn, which is L, is going to be the limit of extends to CF exists and equals to L. So we have also seen that what is the negation of this is if you are able to identify a sequence in A which is distinct from C and that is converges to C, then the image, the sequence of images of this member of sequences f of xn diverges or does not converge to L. There are two things. Diverges, limit does not exist. Does not converges to L means the limit may or may not exist, but if it is exists, it's not going to be equal. Okay, right. So we have seen examples like limit extends to 0, 1 by x. We have seen limit extends to 0, sine of 1 by x. Also we have seen. Okay, so examples we have already looked. Okay.
Sir?
Yes.
So in the third line, we had written limit extends to C, f of x. Therefore, we are trying to get f of C. Therefore, C would belong to A or not.
Where?
In the third line.
Third line means which from the last?
No. Limit extends to C.
limit here.
Yes. We are trying to
C.
get limit.
Yeah.
Yes. We are trying to get f of c here.
No. F may or may not exist at C.
Okay, but limit
May or may
extends
not
to
be
c.
defined.
Okay, but here c should belongs to a or not. Should belongs to a or not here.
No, I
We had
have
written the
started.
second belongs to R.
No, I have already started with the function which is defined on A, and I have already clear here, make it clear that C is a real number, may or may not belongs to A.
Okay.
Okay, so because there are sets. For example, if you have missed the set, like if A is the set 1 by n such that n belongs to natural number. Okay, 0 is the limit of this sequence. If you look at here, limit of 1 by n is 0, but 0 does not belongs to A. Okay, if you take this example, A is equals to this, 0 does not belongs to A, but 0 is a cluster point of A. Okay,
Okay. Yes.
okay, so if it happens like limit exists, okay, and you are trying to say f of c that is equals to f of c, that is the case of the next, right? Means whenever this was only possible when f is defined as c. So first of all you have to make it clear, okay, whenever you're talking about limit, C may or may not be the part of A. But if you go for the next step, it's like, well, suppose C belongs to A, whether this exists and equals to f of C or not, that is also a question. Okay, I can give you the example, okay, where it may not happen. For example, I'm just giving you the example. We will get in the detail maybe later on. Let's say example is I have defined f of x is equals to sine x for x non-zero, and let's say 2 when x equals to 0. Okay, so f at 0 value is 2. It is given to you. But when you are trying to identify limit x tends to 0 f of x, it is 0. It may or may is not equals to f of 0. So this again depends on the definition. So sometimes you will find this is the prototype of the problems, like you will find out in the GATE exam as well. Okay, they will identify this number as some k. They will give the definition and ask you for what value of k. If you replace this 2 by 0 here, this function becomes, you can say, continuous. Okay, that's a part of later on. Did you get my answer?
Yes, sir. Yes.
Okay, so limit, first question is limit may or may not exist. If it exists, it may or may not equals to the function value at that point. Okay, first of all, function should be defined at that point. Then only you can say C is a part of it. Okay?
Yes.
Okay. Now, what we are going to do is, now once we know the sequential criteria for identifying the limit, then we can apply the similar results what we have observed during the session for sequences like squeeze theorem. Sum of two sequences converges if x and y converges. The two sequences are given, x and y. If they both are converges, their sum will converge to the sum of the limits. Difference will converge to the difference of the limit. Product will converge to the product of the limits, and so on. We have seen some of the algebra of the sequence. So similarly, we can also apply the similar results there, and we will obtain the similar results here as well. Okay, now other point is we have also talked about if a sequence is convergent, then it is necessarily bounded, but the converse may or may not true. Okay, so here also we are going to look after the result, but now see, you are if you look at in the graph. So whenever you are talking about x value is going to be lies on the some domain on the x-axis, and the corresponding f of x may be here on the y-axis. Okay, right. So you have, this is a, let's say this is a point C, where function may or may not define. We don't know. So it may be breaking here. Okay, it may not be. It may be continuing here. We don't know. Okay. Now, what we want to look for is whether the function remains bounded in some neighborhood of C or not. It may or may not be possible that function is bounded for every neighborhood of C. It may or may not be possible. But can we talk about it? There is a neighborhood of C over which the function is bounded. Okay. So this we are going to try to get an answer for this the next day. Okay. Right. And then it will be useful in many applications. Okay. Now, so first we are going to define the boundedness on the neighborhood of C. So any neighborhood will be looks like what? C minus delta to C plus delta. Because on x-axis it looks like the open interval. We are talking about only open neighborhoods. Okay. And what? So we are going to see whether the function is bounded on this neighborhood or not. So first of all, function may or may not be defined at all of the neighborhood. So that's why it is necessary to take the intersection with the set, the domain. Okay, so that the function is well defined over it. Okay, so this is what here. This is what this here. So if you are able to identify a positive constant m such that we have mod f of x is less than equals to m for every x in this neighborhood of C, then you will say f is bounded on a neighborhood of C. So if for some delta, means it may you have to identify that delta. So delta is greater than 0. For some delta this should happen. Then you can say that f is bounded on a neighborhood of C. On a neighborhood. It is never be a the. Okay, on the neighborhood, it's going to be a neighborhood of C. Okay, if there exists a delta neighborhood of C and a constant m such that so and so happens. So this is what the meaning is. F of x remains bounded. What is the meaning of bounded? Means it lies inside an interval. So if you go back and here, so what is so over which this is going to be, you can say minus m2 plus m. So here, so this is minus m and this is plus m. So f of x lies between this interval of the y. That's what it means. Okay. So if you open up the definition of absolute, mod f of x is less than equals to m, means minus m less than equals to f of x less than equals to capital M. And that is lies on the values on the y-axis. These are the x-axis. Okay, right. So this will be the definition of boundedness of a given function f on a neighborhood of C. Okay, right. So when this should happen, we have one result which is as follows. If A is a subset of R and f from A to R has a limit. Okay, so the only thing is you need to have is limit x tends to C, f exists. If this happens, limit x tends to C, f exists, then you can certainly find out a neighborhood on a neighborhood of C over which the function is bounded. It's very interesting. You can see whenever limit x tends to C, f exists means what? For every epsilon, there exists delta greater than 0 such that mod of f of x minus L is less than epsilon whenever 0 less than mod x minus C less than delta. If you recall the epsilon delta definition. So this should have, this will going to be happen for every epsilon exists, and let's say this is equals to L. So I'm talking about the equal to L. Now this is happening for every epsilon. You are able to identify delta. So you can fix now epsilon and you can work. Okay, right. So how? So if I wish to go with the proof here, it's a very small proof. So solution So you can take let epsilon is equals to any number. So in reference book, you have been seen that it's going to be 1. It's not restricted to 1. You can take 1 by 2. Okay, epsilon equals to 1 by 2. Then there exists delta such that mod of f of x minus L is less than 1 by 2 whenever 0 less than mod x minus c less than delta. Okay, right. So this is this now from here. Now use this result now. So this is a dilated neighborhood of C, but you know that C or may not be the part of A. Okay, so if this is true means like this is going to be x belongs to A intersection in terms of neighborhood that V delta of C. Okay, so what it implies is now use the triangle inequality mod f of x is equals to add and subtract L and use the triangle inequality less than equals to mod f of x minus L plus mod L. Now this is certainly less than mod L plus 1 by 2 for all x in A intersection V delta. That's it. So this is this you can treat as M and this is a neighborhood of delta over which the f remains bounded. Now you can discuss whether that C is a part of A or C does not a part of A. That you can discuss and you can create artificial M for the same. Okay, so this is the step 2 for proving the above result. But the above result guarantees that if the limit extends to CF exists, then it is going to be be bounded on some neighborhood of C. Okay, right. Now, I hope you have been aware of that how to identify the sum of two functions, difference of two functions, product of two functions, scalar multiple of a function, okay, and division of function. Okay, this is the definition of that how you define the sum, how you define the difference, how you will define the product, how you will define the scalar multiple, how will you define the quotient of the two functions. Okay, so I hope this is very clear. The sum of two function is f plus g of x, f of x plus g of x individually in a linear, you can say in a linear manner. So f minus g means you take individual value and make the difference in the same order, f of x minus g of x. If you have g minus f, g of x minus f of x. Similarly, f g, so not that, I'm talking about the product, I'm not talking about the composition. Okay, for the composition, we have the notation with small o. Okay, that is a separate thing. F compose z of x is equals to f of g of x. Okay, so f into g, you can take the individual values and make the product. Obviously, they all are defined to be on the common domain. Okay, that we are calling as A. If it is not, you have to take the intersection of each of the domain. Then only these things are well defined. Okay, right. So further, if here is the scalar multiple, so b into f, scalar multiple of the function. How will you define is b f of x is equals to b time f of x. You take the values and multiply by quotient. You will define by f of x by g of x in the quotient manner, provided g of x should not be 0 for any value of x. So that condition need to be put. Okay, now what can you talk about in the limit? So suppose you know that limit x tends to c f of x is L. Suppose you know limit x tends to c g of x is some capital M. What can you tell about the f plus g or f minus g or f into g or scalar multiple or quotient? Okay, so that is again can be answered in the similar manner. The proof is exactly the same what we have done for the algebra of the sequences. Okay, if you are going to use the sequential criteria. If you're going to use the epsilon delta definition, the proof is also again going to be the similar. Okay, so I'm not going to give the proof for that. I'm just stating the result. How will you go for the limit of sum of two functions, difference of two functions, product of two functions, and so on. So here is that. So first of all, let f and g should be defined on the common domain. That's very necessary first. Okay, then the next thing is the C belongs to R be a cluster point of V. That's again the next thing to be verified. And this B belongs to R, that is for scalar multiple, so that we will see later. Suppose limit x tends to C, f is L, okay? X tends to C, f is L, and limit x tends to C, G is M. So whenever we are writing in this fashion, it's like limit x tends to C, f is L means it's obviously assumed that limit exists and it is equals to so value, that L value here. In this case, M value here for G. Okay, so this is the first starting one or starting with. First, you have to verify that whether both the limit exist or not. Okay, then only you can proceed with the algebra. So then limit x tends to C, f plus G is nothing but the sum of the limit, difference, so difference of the limit, product of the limit, scalar multiple of the limit. It's very simple now. So if you have sum of two functions, like you have x to the power n or x square plus 3x plus 1 now. Okay, it's a polynomial of degree 2. Okay, so you can treat this function f, you can treat this function g, you can treat this function h. They all are well defined over real number. So as x tends to 0, f of x tends to 0 exists, that we have already shown. Limit x tends to 0, g also exists, that is also 0. Limit x tends to 0, h exists, and that is equals to 1. So this result will tell you the limit of this function is going to be sum of the limits. So 0 plus 0 plus 1. Okay, so now you can talk about any polynomial or any like x plus let's say sine x function and so on. Okay, different type of functions. Okay, where you can first you have to verify that these things are there. Okay, now regarding the quotient rational function, you can say, okay, the rational function is like f of x by h of x form. Okay, like for example, you have let's say x square minus 4 divided by x cube plus 1. Okay, for example this. So again for given epsilon, create artificial delta. So these type of functions are not that easy. Okay, you have to work over the range of x and so on, so many things. Okay, however, you can refer the result. Okay, if x is from a to r, if h of x is non-zero, means you need to verify whether this is going to be non-zero for all x in a. Okay, and if the limit is also non-zero, that also need to be verified. Okay, if the limit of the denominator, we are only focusing on the denominator. So if the limit x tends to C h is capital H, which is non-zero, then you can go for limit x tends to C f by h is equals to L by h. Okay, so here you need to keep your eyes on denominator. Provided first you have to verify that numerator is the limit of the numerator exists. Okay, after simplification or without simplification, suppose that f is limit is exists. Okay, and now you have to focus on the denominator of the rational function. If the limit exists and it is non-zero for every x in a, and if the limit is also non-zero, then you can refer the result and you can say that limit of this is going to be the L of. So if I want to say what is the limit of x tends to 0, so I know that limit x tends to 0, x square minus 4 is equals to minus 4. Similarly, limit x tends to 0, x cube plus 1 is equals to 1, and which is non-zero. And also this is non-zero for any x in a. So this is going to be minus 4 by 1. That is going to be minus 4 by referring this result. So now it becomes the life is so simple. Only you need to verify about the numerator and denominator separately, some of the conditions. Okay. Now these are the results. What I am going to state now, they are going to be can be proved in the similar fashion as we have done for the sequence case. Yes.
In the previous question, if we take x tends to -1, then what happen?
Tends to -1. See, this x tends to -1, this denominator becomes 0. So you can't refer this. You have to go with the epsilon delta or some sequence case and so on. So,
Okay.
of this, the domain should not contain -1. That you clear. Okay. And where the function is defined f and h, both should both or means that this rational function completely should not contain the -1 point. Otherwise, because you cannot refer this result, because this clearly conditions are clearly stated here. H of x should not be 0 for every x, and limit should not be 0.
Okay, sir, I get it.
Okay. So you have already seen whenever the sequence is such that a less than equals to x less than equals to b and the limit exists and equals to c, then a less than equals to limit of xn less than equals to b. You can use the sequential criteria here. Okay, and to establish this result. So whenever you have seen that f of x is a bounded, means in other words that a and c, whenever you are writing a less than equals to f of x less than equals to b, for some points a and finite numbers, equal to sign is there. Okay, they are not infinity or minus infinity. That's very first case thing. Okay, now if this is there, means f of x lies inside the closed interval a to b. Means the situation is like you have the function is there. So now suppose this is your y equals to a, and let's say this is y equals to b. So this is the situation. Now if you talk about of c here for every x in a, x not equals to c, then if the limit exists, then where the function is like you have, this is going to be this only, but and this can be analyzed geometry as well, that limit is also lies inside the A. It cannot go away from the B, neither from A. Okay. So the squeeze theorem tells you that if you are able to identify three functions in the following relation, f of x less than equals to g of x less than equals to h of x, means they are comparable, you can say. For every x in A, x not equals to c. And in addition, what you have the property attached with that is limit of at c is L and limit of h at c is L. Okay. At c. Then the squeeze theorem tells you that limit of g also is L at x equals to c. There is a g, limit of g will not go anywhere else. Okay. For example, I have taken this example that minus x less than equals to sine x less than equals to x for every x greater than equals to 0. That I wish minus x less than equals to sine x less than equals to x for every x greater than equals to 0. Okay, that we want to clear. Now we know that the following fact, we know that minus 1 less than equals to cos x less than equals to 1 for every x in R. So if you integrate this minus 1 0 to x dx and integration 0 to x cos x, integration 0 to x 1 dx, they will also be related with the same inequality here because of the fact that for x greater than equals to 0. Now, once you perform this, give you the establish your result that minus x less than equals to sine x less than equals to x. Okay. Now, what is the comment here is main is that integration will follow the monotone property. That okay means if f of x is less than equals to g of x, you will you will be more clear when we will discuss Riemann integral. Okay, so it will come at later stage. Okay, so by using the previous result, if x is less than equals to 0, then minus x is greater than equal to 0. So I can apply the I can use the result for minus x, and I can find that for x less than equals to 0, you will have the same this inequality, and which is as like x is less than equals to minus sine x less than equals to minus x for x less than equals to 0. Certainly, this will implies certainly minus, if you multiply by minus, this minus x is greater than equals to sine x and greater than equals to x, right? For x less than equals to 0 means x is less than equals to sine x less than equals to minus x for x is less than equals to 0. So this is going to be, I'm just going to identify now f of x is equals to minus x is greater than equals to x if is at x equals to 0. So it's going to be mod x function, right? It's going to be minus mod x, right? Minus times mod x, right? And if I identify g as x for x less than equal to minus x for x less than equal to 0 is going to be mod x, and your h function is sine x. Okay, and your h function is sine x, then and your h function is sine x. Then from above results, about two results, two inequalities, what you will establish is f of x less than equals to h of x less than equals to g of x, right? What is f of x is minus mod x, g of x is mod x, and h of x is sine x. So f of x is minus mod x, g of x is mod x, h of x is sine x. And you know that limit of f as x tends to 0 is 0, limit of g as x tends to 0 is also 0. Then Sequential theorem tells you that limit of h also tends to 0. So limit x tends to 0, f is equals to 0 is equals to limit x tends to 0, g. So then Sequential theorem implies limit x tends to 0, h is also 0. Okay, right. So this is an example of the Sequential theorem.
Yes, sir. Sir, I have doubt.
Yes.
Previous slide.
Yes.
Yes, in the previous slide. Here you have written from blue ink implies minus x is greater than sine x greater than x for x greater than 0. No?
No, for x less than equal to 0.
Then how you have defined this fx?
F of x is minus x if x is greater than equal to 0. Okay, and f of x is x if x is less than equal. So for this left side I am identifying. So if you previously see minus x less than equal to sine x less than equals to x for every x greater than equal to 0. Okay, so
Okay, yes, got it.
Fine.
Yes, fine. Okay.
Okay, right. So similarly, we can use other results. Let's see whether we have the examples or not. Okay, yes. So let's see the first example here. Limit x tends to 2, the following limit. Value is given to be 20. Prove or disprove the following. Now, recognize both the functions in the product. X square plus 1 is a polynomial. X cube minus 4 is also a polynomial, and they are sitting in the product. So there is no discussion about some one of the limit is 0 or non-zero because it's not writing in the rational form. We are not worried about that much now. Now further, what you need to only show is limit x tends to 2, x square plus 1 is exist, and that is equals to 2 square plus 1, that is 4 plus 1, that is 5. And limit x tends to 2, x cube minus 4, and that is equals to 4. And now you refer the result from the algebra of the function, right? Limit of f exists and equals to L, limit of g exists and equals to M. Then product will give you the L into M. F5 into 4 is 20. So you can again, you have to just show that limit of x tends to 2, x square exists and x cube exists. And then you can take this f and this f1, this is f2, this is g1, this is g2, and you can show that limit x tends to 2, the algebra of limit also you can apply. Okay, instead of going with the epsilon delta. Okay, now if you look at the second problem, so this is again just behave in the similar way. So if you see the denominator is x square plus 1, so it will never be 0 on the real line. Okay, for any value of x. So we are not worried. So note that limit x tends to 2 numerator exists and limit x tends to 2 denominator also does exist. And they both are equals to, so above will equals to 4, the limit, because 2 cube minus 4 is 4. The denominator is x square plus 1, that is going to be 5. So it's going to be ratio of this only 4 by 5, because they have put in the, instead of product, we have put in the rational. Okay, so here we should be worried about the denominator much, so that this should not be 0, and this should not, the limit also should not be 0. Now, the third question here, if you look at limit x tends to 2, x square minus 4 divided by 3x minus 6. So if you take it as it is, x square minus 4 by 3x minus 6, if you limit of x tends to 2 is 4 minus 4, that is 0. The denominator 3 times 2, 6 minus 6, that is 0. And that is going to be 0 at 2. Okay, so you cannot refer the result here directly. What you can do is you can simplify this function. So you can write above one is x minus 2 into x plus 2, and the denominator is 3 times x minus 2, so x minus 2 get cancelled. So you will have only the simplified form of here is going to be x plus 2 divided by 3, and that you are going to evaluate limit x tends to 2. Here you can refer that rational result. Okay. We will come back to this fourth problem because we want to show that limit does not exist in R. So one thing we can comment is limit x tends to 0, 1 exists. It is constant limit is constant. Now denominator x tends to 0, x, if you look at that exists, but it is equals to 0. So you cannot refer that rational one result. Okay, so that algebra cannot be utilized here. Okay, what can be done here is, again, you will see some another result. Already you have seen sequential argument. You will see one more argument. Okay, right. We will come back to this fourth problem. Let's to understand this problem. Limit x tends to c, the p of x is p of c, where p of x is a polynomial. So whenever we are saying this a polynomial means this is a form n degree polynomial where all the powers of x is positive. And we have already shown that limit, you can show that limit x tends to c, x to the power n is equals to c to the power n. Okay, you can show that by using the argument of algebra, because you know that limit of x tends to c, x is c. You can show that this. Now you can write x into x to the power n as x into x into x into n times. Okay, once you show limit x tends to c, x is c. Okay, that is very easy to show. Okay, now next you can use the result now from the algebra of the limit. You know that limit x tends to c, f into g is going to be the the product of their individual limits. So x is sitting product is n time. So the limit as also is c into c into c n times. Okay, if you use the algebra of the function. Okay, so limit x tends to c x to the power n is c to the power n. Now you can use the sum of two functions. So here n plus 1 terms will be there in n degree polynomial. Okay, you can use the above facts that algebra of the two function. How will you perform? Okay, that will be very simple. Write a general polynomial and use the fact that limit x tends to c x to the power n is c to the power n, and you can use the scalar multiple how they behave and addition in when you done. The sixth problem is limit x tends to c the rational function again. So where numerator and denominator both are polynomials. So we have already seen two examples here. One example is in second example, one example is in third example. Okay, so whenever px and qx are polynomial and q of c is non-zero, so whenever you have the numerator and denominator, okay, when you have the function a rational type, okay, and when the numerator and denominator are polynomials, then you have to no need to worry about any other points. Only you have to worry about the points where the denominator vanishes. So you just find out, identify the point where the denominator vanish. So if you look at here, denominator does vanish at x equals to 2. Here, if you look at, denominator will never vanish on the set of real. Okay, so whenever the numerator and denominator are both are polynomials, then you have to look for the points where the denominator vanishes. Now, then you have to see whether that is equals to c or not. So at c, whether the denominator is non-zero. Or you can say that that point is the root of the equation q of x equals to 0. Okay, so if that is not there, then you can certainly, this is nothing but the limit, nothing but the numerator and denominator, the polynomial, are evaluated at c only. Okay, so you can use this result in various form now. Okay, so you can have very high degree polynomial now, 100-degree polynomial as well, px, and qx also 100-degree polynomial or 99-degree polynomial. And you have to just verify whether where the limit x tends to c, whether that limit value is the 0 of the denominator or not. That's what the importance here. Okay, not other than point. So whether in the other name, whether there is any 0, you can always work out with that. That's what the idea here. Okay, right. Now look at the seventh problem. Limit x tends to 0, x to the power 3 by 2 equals to 0. So far we have worked with the integer power. What about the x to the power 3 by 2? Can you apply the squeeze theorem? You can certainly go with the epsilon delta. There is not a problem. It's very simple to follow the epsilon delta definition for a given epsilon. There exists so and so.
Sir, can we use here x into x to the power 1 by 2?
Yes, certainly you can.
By multiplying the
Yes.
two functions.
Yes,
Okay.
x into root x. It's nothing but x to the power 3 by 2 is x into root x.
Root x, yes.
So you know that limit x tends to 0, x is x, 0. But what about limit x tends to 0, root x?
That would also be certainly 0. Root x, limit x tending to 0, root x would also be 0.
That need to be proved.
Okay.
So that for that you are going to use the this epsilon delta definition. If you are with this argument, what you can see is limit is x tending to 0, whether you are coming from the left or from the coming to the right. Now, what is assured is x can never cross 1, means it will never coming after 1. Okay, because it will never reach to 0 otherwise. Are you with me?
Yes, yes.
Okay, so x should be lies between 0 to 1.
Yes, sir. So we can apply a squeeze theorem.
Yeah, squeeze theorem we are going to apply. So whenever x lies between 0 to 1, we certainly have,
X raised to 3 by 2 less than x.
so for, yes, for 0 less than x less than equals to 1. Okay, or you can say certainly strictly less than 1, less than 1, we have x is less than root x. Right, less than equals to 1 we are also possible for this case as well. X less than a equals to x less than root x, right? Can I say this? Whether this inequality true?
Yes, sir.
X less than root x, and certainly this is less than equals to 1. Now what you can do is, this implies multiply x. So you have x square less than x to the power 3 by 2 less than equals to x. Now this tends to 0 as x tends to 0. This tends to 0 as x tends to 0. So squeeze theorem gives you guarantee that this also tends to 0 as x tends to 0. So there is no known of epsilon delta now, because we are known both limits. Limit x tends to 0, x square we know that is going to be 0. Limit x tends to 0, x also 0 we know. So squeeze theorem certainly tells you that this is going to be 0 as x. Okay. See, in the squeeze theorem, they see this. This you should not be restricted, right? This should be this greater than equal to sign must be there, and so on. You should not be particular about it. This may or may not be, but it is lies. This behavior will not change in the limiting sense. Okay, so if you want to claim that limit x tends to 0, root x is 0, we should have some claim here. We have not said so far that if f of x to the power, let's say p, suppose this is f of x to the power p is there, some p is any, you can say p is any greater than 0 now, and suppose limit x tends to c f of x exists and that is equals to L, then limit x tends to c f of x to the power p is equals to L to the power p. We have not made such comments so far I know x to the power for integers we know, because we can write down in the product and we can do that. But for positive integers, for natural numbers, you can say particular. Okay, but for fraction power, we have not commented anything so far. And we don't have any supported result here. So what we can do at most is, instead of going with squeeze theorem, you can certainly establish greater than 0. You can go with root x minus 0, and we want to show this is the limit that is less than epsilon whenever 0 less than mod x minus mod x less than delta. So certainly mod x less than epsilon means mod of root x. X certainly should be greater than 0, so that it should be well defined. So you can only talk about here 0 plus, you can say. You can talk about 0 minus, because it is the square root function is not defined. Only you can talk about the right hand limit, not left hand limit. Yes, right?
Sir.
Okay,
So,
then this x is less than epsilon. Here, you know that a less than b, whenever a and b are greater than 0, then a to the power n is less than b to the power n. So then you can take delta as epsilon square. So you can use the epsilon delta definition for establishing this result as well.
sir.
Yes, question.
Sir, so I cannot get when to prove, means suppose like we are here giving an argument for limit root x equal to 0. So for example, we use that limit 1 upon n equal to 0 or limit 1 upon n square equal to 0. For that also we need to show by this squeeze or that epsilon delta definition that it actually is 0, or just we can write that at n tends to infinity. So limit 1 upon n square is 0.
See, whenever you are going to establish a result, okay, that means like whenever writing a solution for a particular problem, you should in the steps you should be that step should be referred, means by a theorem. by a result, what you are going to means you have to state that result. Theorem like squeeze theorem, you can simply say squeeze theorem. That's because this is standard. You can say this is from squeeze theorem, the result follows. No need to write f, z, and h and so on that complete result. Now the come is next is your argument is like 1 by n is limit is tending to 0. Thus we have to do all the things. See, when you are doing some assignment, okay, suppose you are in assignment problems. Okay, suppose at some problem during some problem, or suppose two problems are there where you are going to use limit of 1 by n is or 1 by n square is 0. One of them is 1 by n square. Suppose you are using limit x tends to n tends to infinity, 1 by n square is 0. Okay, then at least one of the problems should contain the proof. Okay, then you can refer from the problem number 1, it is true. Okay, okay, you understood my point. Whenever you are writing the exam, suppose you are in exam. So in an exam, you are supposed to. Okay, because see, because I want to understand why this should limit goes to 0. I cannot take, it's obvious.
Okay.
Okay, some of the things like see things, something will be easy. It's right referring this result, stated results. You are referring Archimedean property. You are referring density theorem. You can referring squeeze theorem. You can referring other comparison tests. Okay, we ratio test. We are the other tests. Okay, so if you are referring the standard result, just writing by the name, that's okay. But if you are referring some the comment like limit 1 by n is 0, since this is 0, yes, true. But how? I want to understand whether do you really know or not, or you just means like by looking at somebody else copy and you just write it that limit 1 by n is 0. Okay, so you need to give some of the explanations. You can use Archimedean property, you use other comparison tests. I don't mind. So I have seen here 2-3 flavors of proving the same result. So you go with anyone. I don't mind with that. Okay.
Okay. So
Also,
suppose if we are using squeeze, then we can just write in the bracket using squeeze theorem. No need to write that
yes.
1 upon
No,
n
no,
is
no,
less than this and
no, 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 no.
okay.
No. Squeeze theorem is squeeze theorem, standard.
Okay.
Okay, that's a standard. That's very well known. I'm not going to ask you what is squeeze theorem. You just tell me. At least in exam, when you are writing the exam, whenever you are suppose you are giving the viva for project or something is there, so I can ask what is the squeeze theorem you are using. I can ask you some of the explainer comments. I don't want to ask you the complete statement. Otherwise, exam will not be completed. So let's complete this. The eighth problem. This eighth problem here is going to use again the results for what we have seen just now. Okay, like previous, I'm just going to previous slide. If you integrate one more time and you can establish the result, that I'm just going to write it further. So you can certainly show that. So I'm just going to leave it for you that it can be proved that 1 minus x square by 2 is less than equals to cos x less than equals to 1 for all x in R. I'm not going to, you see, you may argue that, sir, we can use L'Hospital rule, but so far we have not done. So you can't. And one of the things is this problem is a standard problem for the GATE exam. So you see this problem, it will be happening in many GATE exams. Okay, so some of the time it's a very standard problem, so it will be coming straightforward. Okay, so from here you can certainly have this implies minus x square by 2 is less than equals to cos x minus 1 less than equals to 0 for every x in R. Right, now depends on x. Okay, or you can say because we are going to divide by x now, so this implies this implies, because we want to see what about cos x minus 1 by x, right? Yeah. So what can you do here is minus x by 2 less than equals to cos x minus 1 by x less than equals to 0 for every x greater than equals to 0. And whenever this is minus x by 2 is greater than equals to cos x minus 1 divided by x greater than equals to 0 for every x less than equals to 0. So again, you will follow the similar argument. You can define f of x is minus x by 2 whenever x is greater than equals to 0, and 0 when x is less than equals to 0. And g of x is 0 whenever x greater than equal to 0, and x minus x by 2 as x less than equals to 0. And this is your h of x. Okay, and you can apply the squeeze theorem in both the cases as limit x tends to 0, this tends to 0, this tends to 0. And you can apply squeeze theorem implies limit x tends to 0 cos x minus 1 by x is equals to 0. Right? Squeeze theorem implies the following. This is equals to 0. Okay, that you have already seen this result already by using L-Hospital rule, maybe in your intermediate session. Okay, so the proof of this result, okay, that again you can use the monotone property of the integral, and you can mistake.
Why here have we taken x square by 2 means we can also take only x square or x cube?
Where?
Means in the starting of the
Here, this one. You're talking about this one? Are you talking about this one?
Yes, sir. He said that we took 1 minus x square by 2 less than cos x. We could have taken something else like 1 minus x square, 1 minus x cube. Why 1 minus x square?
Yeah, because I have told you, right, how this result is going to come is you are going to integrate this one. So minus x integration is minus x square by 2 less than equals to minus cos x, limit is 0 to x, and you are going to use this fact here. Okay, so if I'm going to integrate this, so let me give you this. So this is the result which you can make it true for every x in R. Okay, so because in this case, whether x is less than 0 or, so see, minus x, I know less than equals to sine x, less than equals to x, or x greater than equals to 0. Now, this implies minus integration 0 to x dx is less than equals to integration 0 to x sine x dx less than equals to integration 0 to x dx. I'm again integrating. So what you will get is minus x square by 2 is less than equals to integration of sine is minus cos. So cos x minus 0, right? And with minus sign. So 1 minus cos x and less than equals to x square by 2. Okay, right. Now from here, what you can observe, this will be like you just subtract 1. Okay, so you have minus x square by 2 minus 1 less than equals to minus cos x less than equals to, you have, this is going to be x square by 2 minus 1. Now if you multiply both sides by minus, what you will get is 1 minus x square by 2 less than equals to cos x less than equals to 1 plus x square by 2. Now, since you know cos x can never go beyond 1, so you can certainly have this is less than equals to 1. Okay, and you have this following inequality. So whether you have x is positive or x is negative, this still remain unchanged, right? Because cos of minus x, cos is a even function. and x square is also even function. So nowhere it will make change. So that's why this inequality is true for every x in R. Okay? Or
Excuse me,
you can-
sir.
Yes.
From the third step, can't we directly divide it by x?
Third step, where in this
Third,
equation?
yes, that from that step, can't we divide the equation by x?
You can, not a problem.
So that we know that minus x by 2 at the limit x tends to 0 is 0 and x by 2 at x tends to 0 is 0. So from
Yes.
that also we can do it.
Yes, you can do it.
Okay, sir.
Yeah, that's also fine. Okay, and this result is still this result is also true for every x in R. So whether x greater than 0 or less than 0 doesn't matter. We have started with 4x greater than or equals to 0, but this result, because of this even because of cos function is even function. So this remains true for every x in R. Okay, right. So then you can still divide by x, and then you can apply the limit. So whenever x is less than 0 and greater than 0, you have to look at it carefully. Okay, when x is less than 0, so left hand limit and right hand limit. Okay, so x less than 0, then this inequality will change. And x greater than 0, this inequality will remain same. Okay, that you need to be careful. You can apply squeeze theorem. Not a problem. Okay, right. Now, what is the last problem is, this is the last problem, ninth problem. Limit x tends to 0, x times sine of 1 by x. So see, we have already seen that sine of 1 by x limit as x tends to 0 does not exist. But if you multiply it by x, this does exist and equals to 0. That you can prove by using again sandwich theorem. This squeeze theorem. Okay. So what we had is I know just now we have already shown that minus mod x is less than equals to sine x less than equals to mod x for every x in R. We have shown that f of x is less than equals to g of h of x less than equal to g of x. Okay, right? So this implies this is true for every x in R. Right? Also, not that we have also minus 1 less than equals to sine x less than equals to 1 for every x in R. Which one is in our favor? We are going to use the same. So see, so whether it's 1 by x or x, this will remain unchanged. Still, it's going to be for every x in R. Because x in R, whenever x is non-zero, it's going to be 1 by x is there, and 1 by x, we can talk about the 1 by x. Okay, so sine of 1 by x is also lies between the interval minus 1 to 1, whenever the things are fine. Now, this implies multiply by x times sine of 1 by x less than equals to x. Now, note that for x greater than equals to 0. Okay, for x greater than equals to 0, this result is true. Now, for x less than 0, for x less than equals to 0, you have this is going to be minus x greater than equals to x times sine of 1 by x and greater than equals to x. For x less than equals to 0, you have this. Or in general, if you combine it, this is meaning is minus mod x is less than equals to x times sine of 1 by x less than equals to mod x for x belongs to R. Now you can verify that this tends to 0 as x tends to 0. This tends to 0 as x tends to 0. So squeeze theorem tells you this also tends to 0 as x tends to 0. Okay, fine. So we are closing here. Okay, thank you.
Sir,
Yes.
sir, in this question, can we write it like that? It is a product of two different functions, x and sine of 1 by x. Now, limit of sine of 1 by x does not exist, but it is a finite number lying between 1 and minus 1 because sine lies between minus 1 and 1. But value when x tends to 0, x is 0. So we can directly say that 0 into any finite number is 0.
No. You can take example like f of x is x and g of x is 1 by x square.
Yes, sir, but in that 1 by x square is not bounded. Here, sine of 1 by x is bounded between minus 1 and 1.
Okay.
So it will be a finite number. Sine of 1 by x will be finite number between minus 1 and 1.
Mhm.
And a finite number into 0 is 0. So we can say that the function is tends to 0. But in the example you gave, 1 by x square is not bounded. It ranges from 0 to infinity.
Okay. So I'm just going to reference this here. Let f from A to R be such that mod of f of x is less than equals to m for every x in it. Okay, means this is minus f less than equals to f of x less than equals to capital M for every x. Now let g from A to R be such that minus m times g of x less than equals to m times, not m times. So this is going to be, result is going to be, can be verified for everything, right? G of x times f of x less than equals to m times g of x for every x in A. And limit x tends to c, g of x is 0. Then only you can apply the sandwich theorem.
Okay, sir.
Are you getting my point? Because if they are that is not 0, that is minus m and here is m, means m times this positive and this is minus m times. Okay, then limit x tends to c, g of x times f of x is also 0. Okay, now if x tends to c, g of x is some another number k, so this is minus m times k, this is capital M times k. So you cannot use the sandwich. Then you cannot decide what a of x is there.
Okay, sir.
Okay. So still you require that limit g is 0. If then you can direct. That's fine. Okay. So Kanish, did you get your answer?
Yes, sir.
Okay. Okay, then thank you. We are closing here now. If you have any questions, you just please post on Google Classroom or you can write me email. Thank you.
Thank you, sir.
Thank you.